This is a T cell, one of your immune system's defenders. T cells patrol your body searching for anything suspicious, like cancer. Every cell presents proteins called antigens on a platform called MHC. Together they form a molecular name tag called PMHC. T cells scan these tags using their own specialized sensors. T cell receptors, or TCR. If the tag looks abnormal, like one from a tumor, the T cell takes action. This is the foundation of cancer treatments like CAR T therapy. In CAR T therapy, doctors extract T cells from your blood and add a new synthetic sensor called a chimeric antigen receptor, or CAR, which allows the T cell to detect specific proteins on cancer cells. These engineered T cells are then multiplied by the millions and infused back into your body, ready to destroy tumor cells. It's a groundbreaking therapy, but it's not without challenges. Making CAR T cells takes time, sometimes weeks. It's also expensive, and in some patients it can trigger severe immune reactions, like cytokine release syndrome. So what's the alternative? One promising solution is microfluidic devices, or labs on a chip that mimic bodily conditions, enabling precise control of flow and cell interactions similar to real tissues. At the George Lab, we are investigating microfluidic chips to isolate rare T cells that recognize tumor antigens. This is because among the many T cells in our bodies, only a rare few can recognize and kill cancer cells. Let's explore how the device is made, how it works, and how it isolates rare tumor-killing T cells. First, we pour PDMSL, a flexible polymer, into a mold and heat it to harden. Once set, it's removed and bonded face down to a glass slide. A cross-sectional view reveals channels that mimic blood vessels. The resulting device is split into 8 channels of different widths and has a source where cells will be added and a sink where flow is directed through withdrawing a pump. Differing the widths of each channel means that even if the flow rate is the same, the shear or force felt by cells in different channels is different. For example, a thinner channel like 1 means that more shear is experienced than a thicker channel like channel 8. Each channel is lined with cancer antigens so that T cells that strongly recognize the antigen will stick, even when shear is applied. High shear makes it harder for cells to stay attached, so only the strongest binders remain. We measure enrichment, or how many of the stuck cells are tumor-specific, and sensitivity, or how many specific cells we captured compared to how many we started with. High shear gives us better enrichment, more tumor-targeting cells, fewer bystanders. But if the shear is too high, even specific cells get knocked off. So, we're trying to find the optimum shear, and we have 8 different shears or channels to do so. This approach could be faster and more cost-effective than CAR T therapy with less side effects, due to the highly specific nature of T cell binding, allowing cancer therapy to be more equitable and safer. In short, these tiny lab-on-a-chips could hold the key to revolutionizing how we fight cancer.